All right, so this is the part of the class that I think is the best. So this is all about how to draw Lewis structures, how to draw a molecule. I feel like this is a fun part of the class where you're actually producing something. Um, and it has a couple of rules that you need to follow. They're fairly straightforward, and it I think that this is almost like a game that you can practice. So the first step is to count the total number of valence electrons. That total number of valence electrons is a number that you're going to come back to. But you're going to count that total number of valence electrons in that molecule or ion. You're going to identify the central atom and place the other elements around that central atom. You're going to place 8 electrons around each element in the structure, except for hydrogen. Keep that in mind, except for hydrogen, because hydrogen's kind of a rascal. Then you're going to count the number of electrons that were placed in the structure and compare the number of electrons used and the number of electrons actually present. So this is more or less like a check. So you drew the structure. Based on what you plan to draw, is it acceptable? Okay, so now how to draw those. If the number of electrons is equal to the number of electrons actually present, the Lewis structure is fine, it's good, it's done. If the number of electrons used is larger than the number of calculated total valence electrons, modify your structure to include multiple bonds. So like a double bond or a triple bond or something like that. If the number of electrons used is smaller than the number of calculated total valence electrons, place the excess electrons on that central atom. So we'll get into some examples where you're going to do that, and we'll get into some exceptions. Okay, so our first example is NH3. So our first step is to look at our periodic table, which I'm not going to pull up a periodic table here, but play along at home with a periodic table. How many valence electrons around our total, or around all of our atoms? We've got a nitrogen and a hydrogen, another hydrogen, and another hydrogen. How many valence electrons does each hydrogen bring in? Well, each hydrogen is going to bring in 1. How many valence electrons does nitrogen bring in? That brings in 5. So this is 5 plus 1 plus 1 plus 1 equals 8. Okay, so how many total valence electrons are there? There are 8. Which is our central atom? Okay, so this is kind of easy because we've only got 2 different types of atoms. We've got nitrogen and hydrogen. So how could one hydrogen be the central atom over any of the other hydrogens? That's almost a debate that you can have, and it's almost like, well, it couldn't be any of the hydrogens because, well, how could it be one over another? So our central atom is going to be nitrogen. You could also think about this as which atom has the capacity to take on a large number of electrons. Well, hydrogen can only take on 2. So if hydrogen takes on 1 bond, that hydrogen is satisfied. It has its maximum number of electrons. So our central atom is nitrogen. Okay, how many electrons does that nitrogen actually want? Well, it brings 5 to the party. 5 to the party. It wants a total of 8. Okay. How many electrons do each of the hydrogens want? Well, each hydrogen only wants 2 electrons. So whenever we draw this, we're basically asking how many single bonds are there going to be. We've got a nitrogen, a hydrogen, a hydrogen, a hydrogen. So there are, well, this model right here shows all of our atoms. That's NH3. How many electrons have we drawn? Well, we've drawn 3 single bonds. Each single bond corresponds to 2 electrons, 2 more electrons, and 2 more electrons. So that's 6 electrons. So where are our last few electrons going to go? This is an instance where we haven't drawn enough electrons. So we have to put those last 2 electrons on our central atom, our nitrogen. And this is what's referred to as a lone pair of electrons. So that's all that there is to drawing a model of NH3. Those non-bonding electrons, or our lone pair of electrons, that's that 2 there. So there's our NH3 structure. So our next model is COH2. How do we draw this? Well, we've got a carbon, we've got an oxygen, we've got a hydrogen, and we've got a hydrogen. Okay, so carbon is going to bring in 4 electrons, oxygen is going to bring in 6, and each hydrogen is going to bring in 1 valence electron. So we've got a grand total of 12 valence electrons. Okay. Now, with that said, after we've calculated our total number of valence electrons, what's the next step? The next step is to figure out which is our central atom. So when we're looking at COH2, well, we can go ahead and eliminate hydrogen as a possible central atom. So then we're left with carbon and oxygen. How do we figure out which one of them would be this better central atom? And one good rule of thumb that you could use to look at this is which is the element farthest left on the periodic table? Okay, and the answer to that question is carbon. Carbon is the farthest left on the periodic table. And so we can use carbon as our central atom. So if we draw this structure, as prescribed, well, it'll look something like this. Carbon in the center, hydrogen, another hydrogen, and then an oxygen. Okay, so, well, maybe this isn't too much of a problem. After we've drawn kind of our stick figure model of this molecule, well, then we want to go ahead and get 8 electrons around all of our atoms that can take 8 electrons. Oxygen's good, carbon is good, but what about our hydrogens? Each one of those hydrogens can only take on 2 electrons. Okay, so, well, carbon and oxygen are both content. Now, the question is, how many electrons were used in this model? We've got 2 at each of our carbon-hydrogen bonds, so that's 2, there's 2 more, there's 2 more, there's 2 more, so that's 8, 10, 12, 14. So 14, so we drew 14 electrons, we drew a proposed model for our molecule. Sadly, 14 does not equal 12. And this is where we kind of look back at the model that or look back at our total number of valence electrons. So now we have to continue. We have to look at the model that we just came up with. HCHO. We have to look at this model. How many electrons did we draw? We drew 14 electrons. Okay, we had actually 12 to work with. So what does that mean? We went over by 2 electrons. Okay, so when you think about a pair of electrons, 2 electrons, I want you to think about that as basically being like one bond. Okay, so how do we resolve this? So we drew too many electrons, or we drew more electrons than we had to work with. So what are we going to do? Well, what we could do is we could add one bond to our central atom. Okay, so add one bond to our central atom. Well, a bond is coming from something else, so where would that something else be? Each of those hydrogens is good, so we don't really want to mess with that. Our hydrogen to carbon, those are both fine. But what if we put a double bond between carbon and oxygen? That hydrogen is still good. That's still seeing 2 electrons. That hydrogen, or both of our hydrogens, are seeing a total of 2 electrons. Now our carbon, on the other hand, well, that carbon has 2 electrons, 2 electrons, 2 electrons, 2 electrons. So it sees 8 electrons. Now our oxygen, we draw what are known as lone pairs of electrons. And when we draw those lone pairs of electrons, lo and behold, that oxygen also has a complete octet. Okay, so basically what we did was we added a bond between carbon and oxygen, and what did that do to our total number of electrons? There's 2, 4, 6, 8, 10, 12. 12 electrons we've drawn. We had 12 to work with. This model right here, this structure has 12 electrons. I'm going to redraw this. And basically that's our model for COH2. So now we're going to wrap this up with N2, nitrogen. Now this is a diatomic molecule. How many total valence electrons? That's where we're starting. So we've got each nitrogen. Nitrogen is bringing in 5 electrons plus 5 more from our second nitrogen. So we've got 10 electrons with which to work. Excuse me, I apologize. So we've got a total of 10 electrons. Good. Now, what that means is we're going to do nitrogen, bond to nitrogen, put 1, 2, 3, 4, 5, 6. And already I can tell that our central atom of nitrogen, or sorry, since they're both nitrogen, there's not really a central atom, but already I can tell that we're looking at something that's not particularly good at the moment. So this structure that I've drawn is 2, 4, 6, 8, 10, 12, 14 electrons. And, well, lo and behold, 14 does not equal 10. So a little bit of breaking news there, but we've obviously got some foundation with which to work. Now, we've used 14 electrons in this structure, and we have a total of 10 electrons with which to work. 4 electrons is our excess. We kind of saw this sort of similarly on our previous slide, or previous example, where we had 14 electrons, but we only had 12 electrons to work with. That difference was effectively 1 extra bond. So if we have 4 electrons, 2 electrons is 1 bond, so 4 electrons would be fair to say that that is a total of 2 bonds that are going to throw us off. So what's our solution? Well, add 2 bonds to the central atom, or to our central atoms as it would be. So now we're going to change it from N to N, but we're going to add a pair of extra bonds. So what that's going to show us is a triple bond between nitrogen, or between the 2 nitrogen atoms. So now I've got 2. Each one of these bonds corresponds to 2 electrons, so that's 6 electrons, and then 2 more electrons on the right-hand side of our structure. So we're looking at something that's a total of 10 electrons. Okay, so now when we reflect on our model, well, how many valence electrons did we have to work with? Each nitrogen brought in 5 electrons, so we had a total of 10 electrons to work with. So the 10 electrons that we had to work with and the 10 electrons that we drew together, well, that makes us happy. Okay, now we can dissect this molecule a little bit more. We've got a triple bond. What do we know about triple bond? They're short and they're super strong. We've also got a non-bonded pair, another non-bonded pair, or a lone pair of electrons. But that's pretty much all that there is to a molecule like this. At any rate, I hope this is helpful. Remember, this is all about, it's like basketball. The fundamentals are what matter. The fundamentals of starting out with the valence electrons, knowing how to read the periodic table and extract the appropriate information. How many valence electrons does each element bring into the fray? That's going to be very helpful. All right, well, I hope you have a great afternoon, and I hope this is helpful. Thanks.